Now, I am going to discuss the simple situation in which how we can get the limiting state probabilities. This is a simple model in which we have only two states, and this two states model is the very good example, in the sense this can be interpreted as the many situation. For example, you can think of a weather problem in which 0 is for a rainy day and 1 is for the sunny day, and what is the probability that the next day is going to be a sunny day from the rainy day, that probability is A, and from a rainy day to sunny day it is going to be the probability B, and the next day is going to be the same thing whether it is a rainy day or sunny day according to the probabilities 1 minus A and 1 minus B, and you can assume that both the probabilities A and B lies between open interval 0 to 1. In this case, this is a very simple two state model. Like this we can give many more applications can be interpreted with the two state model with the transition probability. This is a one step transition probability with the P matrix, that is the P matrix is the state 0 and 1, 0 and 1. So, 0 to 0 1 minus A, 0 to 1 that probability A, and 1 to 0 the probability is B, and 1 to 1 that is probability 1 minus B. So, this is a one step transition probability matrix, and from this model you can see that it is since A and B is open interval 0 to 1, this is going to be a irreducible Markov chain and with the finite state space. Therefore, using the result we can conclude all the states are going to be a positive recurrent. That can be verified from the classification of the states also. You can verify that the first one is recurrent state, that means you can find out the probability of F 0 0, that is going to be 1, and similarly you can conclude, you can find out F 1 1, that is also going to be 1. So, you can conclude both the states are going to be a positive recurrent, and you can find out mu 0 0, that is going to be a finite quantity, as well as mu 1 1, that is also going to be a finite quantity. Therefore, you can conclude it is going to be a positive recurrent. Now, our interest is what is the limiting distribution. That means, you find out what is the limiting distribution matrix, that is nothing but limit n tends to infinity p power n, where p power n is nothing but the n step transition probability matrix, that is same as the one step transition probability matrix power n. That means, you have to find out what is a p power n for any n, then you have to find out what is the p power n matrix as n tends to infinity. So, you can use either eigenvalue and eigenvector method, or you can use the by induction method. That means, you find out p power 2, then p power 3 and so on, then you find out what is p power n by mathematical induction, or you find out the eigenvalues or eigenvectors, then you find out the p power n. So, here I am directly giving the p power n values matrix. So, this consists of 4 elements with a function of a, b and n. This will exist provided the absolute of 1 minus a minus b is less than 1, otherwise this will not p power n will not exist. Now, we are going for as n tends to infinity, what is the matrix, that is limit n tends to infinity, the p power n is that matrix is going to be, again it is going to be a stochastic matrix, because the row sum is going to be 1 and all the elements are greater than or equal to 0. Therefore, if the limiting probability matrix exists, then it is going to be unique. The limit exists means it is unique, and the row sums are row values are, all the rows are going to be identical, that you can visualize. So, that vector is going to be pi, that is pi 0 and pi 1. So, the pi 0 is nothing but pi 0 is nothing but b divided by a plus b, and pi 1 is nothing but a divided by a plus b. These are all the limiting state probability. That means in a longer run, the system will be in the state 0 or in the state 1, and the system will be in the state 0 in a longer run with the probability b divided by a plus b. In a longer run, the system will be in the state 1 with the probability a divided by a plus b. Note that these probabilities are independent of a initial state I. That means whether you start at time 0 in the state 0 or 1 does not matter. In a longer run, the system is going to be in the state 0 or 1 with these probabilities. So, this is the situation for a time homogeneous discrete time Markov chain with the finite state space and irreducible Markov chain. Therefore, all the states are positive recurrent, and we are getting the limiting state probabilities which are going to be independent of a initial state. So, this information is going to be useful later. Based on this, I am going to distinguish 3 different probabilities distribution. The one is a limiting distribution, the next one is a stationary distribution, the third one is the steady state or equilibrium distribution. In general, all these 3 results are these 3 distributions are different. That is the limiting distributions, stationary distributions, and steady state or equilibrium distribution. All 3 are different in general, but there are in some situation, that means for a special case of a discrete time Markov chain, all these 3 results are going to be same. So, for that this example is going to be an important one. Now, I am going to discuss the ergodicity. This is a very important concept in the any dynamical system, but here we are discussing the Markov process, or we are going to discuss the time homogeneous discrete time Markov chain, but the ergodicity is an important concept for any dynamical system. So, I can give the easy definition, that is it is necessary and sufficient condition for existence of Vj's, that is nothing but some probability state probabilities. If that is satisfying, Vj's are going to be summation Va is Pij, and the Va's are going to be summation is going to be 1 for j. In case of irreducible aperiodic Markov chain, then we are going to say the system is a ergodic system. That means whenever the system is a irreducible and aperiodic Markov chain, and then that system is going to be called it as a ergodic Markov chain, or this process is called the ergodicity. That means if you have a irreducible and aperiodic Markov chain, the ergodicity property is satisfied. What is the use of ergodicity property in the Markov chain? Since it is a irreducible and aperiodic, these limiting distributions, these probabilities are going to be independent of initial state. Therefore, this is used in the discrete event simulation. That means if you want to find out what is the proportion of the time the system being in some state in a longer run, that you can compute by finding that is nothing but the limiting probabilities, and this limiting probabilities same as these probabilities Vj's can be computed in this way using the one step transition probability matrix, and that probability is going to be always independent of initial distribution. That means whatever the seed you are going to provide in the discrete event simulation, that does not matter, and you are interested only in the longer run, what is the proportion of the time the system being in some state. So, that can be easily computed for a ergodic system. That means before you use the ergodic property in any dynamical system, you have to make sure that that system is a irreducible aperiodic, then you can use the ergodicity concept.